Hi, I'm Selvan. Welcome to my YouTube channel. In this one, we will try to understand everything about train test split. Now, when you're building your machine learning model, you need to ensure that your model is capable of predicting equally well on data that it has not seen. Let me say that again. You're building your machine learning model, which is trained on a specific set of data. Right? This model is trained on this particular data. Now, this has learned from this data. Once this model has been trained, it should be capable of predicting equally well on data that it has not seen. That data that it has not seen is what we call as test data. The model needs to perform equally well on both the data it has seen as well as the data it has not seen. The first and the basic method to ensure this is to split your data into train and test data set. Here's the whole flow of how this can happen. So you have the full data set. You have been given a full data set. This full data set contains the features as well as the variable that we want to predict. We will call it as y. The features is the x and the variable that we want to predict is the y. Now, this data set, we want to split it into training and test. You could split it into 70:30 ratio, or you could split it into 80:20 ratio, or 90:10 ratio also. Just make sure whatever way we are splitting the training and test, you have sufficient data points in your training data set. Alright. If you have a lot of data points, you can simply split it into 50:50 ratio also. Nothing wrong in doing that, provided there is a sufficient amount of data points for your model to train on. Alright. Now the split has been done. You have split it into training and test. Now how it works is, your machine learning algorithm will be training on this training data set alone. This data set alone will be used to train your machine learning model. Once this has been trained, we can use only the x variables from the test data. Once your model has been trained, right? Once it has been trained, we will pass in only the x from the test data as an input to your machine learning model. On passing this, it will give us back the output, which is the predicted value of y from the model. So now we have the actuals. This is the actual value of y, which is already present in the test data set. We have the predicted values also. We can compare both of them. And compute an error metric. We can compute the error of the model on the test data set. Alright. Now we have an error from the test. We will call it as the test error. Right. The same process we can do on the training data set also. So this training data set x, we can pass as an input. This will give us back an output that we can call it as train pred, which is the predicted value of this. This is the actuals, right? This is the actual values. This is the predicted values. We can now compare this. This train pred is also called as the fitted values. The technical term for train pred is fitted values. Once you have both the actuals and predicteds, we can compare both of them and compute the train error. So we have the train error from this set of the data. Now you have the test error and the train error. Now what we would expect from a really good model is two things. One is the error is low on both the test as well as the train. Alright, the error is low error. Alright, that's an expectation from a good model. And we want this error to be low or comparable on both the train as well as the test. For example, say your model is able to predict with a 10% error rate on the training data. We would expect the model to be able to predict at a similar error rate. The similar error rate, meaning it can vary from say 5% to 15% or even closer to 10%, right? You should predict at a similar error rate compared to what it does on the training data. If it is predicting with say 70% error, that's too much exaggerated, maybe 50% error on the test data, then this kind of a condition is what we refer to as overfitting. What this means is, it is able to predict really well on the training data set, but it is not able to generalize on data that the model has not seen. To get a more visual explanation of what overfitting would look like, I have googled in here overfitting in machine learning. You can see here there are two cases. It can be for classification problems, say you are trying to classify two types of data points using machine learning. So here this is underfitting. It's not really learning the difference between the data well. This would be an optimal fit for the machine learning algorithm to learn. Whereas if it learns very closely to the data, that is drawing more complex boundaries like this, there's a very good chance that it is not going to generalize well on the data, on new data that is going to be given to this model. So this kind of a situation is what we refer to as overfitting, too much complicated, right? And this is not having enough information to segregate the two classes. This is called underfitting. An appropriate fit like this is what we desire. It is okay to misclassify certain points here, which is okay, right? So this is a classification example, whereas a regression example is over here. A regression example, so the data points here, we have data points in this kind of a non-linear pattern. This is not learned the predicted values of the red line over here, right? This has not really learned the pattern or the pattern between the x and the y variable, right? It has not really learned. It is fitting a plain straight line, whereas this is a good fit. This kind of a fit, a non-linear fit, is a good fit, and this is too much of a learning. This is fitting very closely to the data points, and it might not do well on new data points that might come in. So this is called overfitting with the case of regression, right? With regression, where we are trying to predict continuous variables, and this is an overfitting with classification problems. Let's now implement this in scikit-learn. We are importing train test split. This is present inside scikit-learn.model selection. Alright, in this module, this is present. Just import it, pass in the data, read in the data here. This is how the data looks like. We have already seen this in previous videos. On this one, we are going to use the train test split function, pass in the data set, select what should be the size of the test data set. 20% of the data we are going to pass into test data, and random state equal to 100. So we are going to randomly, in the previous example, in the image, we have split it in this ratio. This is not a continuous mass. What will really happen is, from the entire data set, we will randomly pick certain amount of rows as training data set, certain amount of rows as testing data set. So this randomly chosen, in order to be able to replicate the same randomness, we are going to set a random state. This will give you the output, which is the training data set as well as the testing data set. So in this method, both x and y is present in the same data set. Sometimes you might have your x separately and y separately. If that is the case, you can pass in the x followed by the y. Instead of just passing df, you can pass in the x and the y, and then set the test size and the random state. And this will give you the train x, train y, test y. You can check the shapes. Like here, totally 10,000 data points exist in this data set. 8,000 goes into training and 20,000 goes into test. Alright. Now, one thing you need to make sure, you need to take care when you are splitting your data into training and test is, if your data set is a classification problem where your y variable contains multiple classes, say it contains classes A, B, C, D, 4 different classes exist in your y variable. Let's say your actual data points could be A, B, A, C, A, B, D, A, C, something like this. Alright, it's a mixture of your y column is a mixture of the values A, B, C, D, like this, something like this. Alright. Now, when you are splitting your training and test data set on something, on a multi-categorical variable, right? When you have the data like this, you need to make sure the proportion of A is to B is to C is to D on your training. The proportion of A is to B is to C is to D on your training is similar in the test, right? The proportion of A is to B is to C is to D in the test data and the training data should be similar. That you can ensure just by passing one single argument called stratify equal to true, stratify equal to y. By setting this, so y here is true, by the way, right? So by doing this, you can ensure the proportion of the different classes in both your train as well as the testing data set is the same. So this is one caveat. The second caveat is, when you are dealing with time series data, when you're dealing with time series data, there's a time element, there's an ordered element, ordered time element to this. So you have your data here, all right. You have your time in the index, all right. You have your time, you have the date or minutes or second, whatever it is, and you have the data. When you're splitting this, we should not be doing a random split. You cannot use the train underscore test underscore split function. Don't use this when your data set has a time series, or if it's a sequence data, time series data or a sequence data, you should not use train test split because it is going to randomize the data. In such data, the order of the data matters. So just simply, if you are going to cut it in 80:20 ratio, just take the 80% of the data points continuously from here, from the beginning, as your training data set. Right? Don't do any sort of shuffling, and the remaining test data, remaining 20% of the data can go into test data set. So those are the two caveats you need to take care of whenever you do train test split. See you in the next one. Bye.